Obviously, it's important to select the proper control valve and size it correctly for each application. In addition to knowledge of how control valves work, proper selection and sizing of a control valve requires an understanding of the principles of fluid flow. You need to be familiar with the types of fluid flow. This drawing illustrates a flow regime called laminar flow. Looking closer, you can see that fluid flows in parallel layers, with fluid near the center of the stream flowing much faster than fluid near the walls. If the velocity of the fluid were measured at various points across the pipe, a flow profile like this would be revealed. The second major type of fluid flow is called turbulent flow. Turbulent flow is characterized by eddies that cause complete mixing of the fluid. There are no distinguishable layers. The velocity profile for turbulent flow is relatively flat. As the overall velocity of a given fluid stream is increased, a point is reached where flow makes a transition from laminar to turbulent. Of course, velocity is only one of several factors that affect the type of flow that will occur in a system. Other factors include the fluid density, the fluid viscosity, and the pipe diameter. These can be combined into a formula that will yield a dimensionless number called the Reynolds number. A low Reynolds number indicates that laminar flow conditions exist, while a high Reynolds number indicates the presence of turbulent flow. It's important to know the type of flow that exists in a system because it affects the precision of the flow calculations used for valve sizing. To explain why this is true, it's necessary to look at the basis for these calculations. We'll begin by looking at liquid flow through a restriction. In an ideal situation, the fluid is incompressible and its velocity is high enough that flow is completely turbulent. In such a restriction, the total energy contained by the fluid will remain unchanged as it passes through the restriction. However, there are some energy trade-offs. As fluid passes through the restriction, the cross-sectional area for fluid passage decreases. Since the same amount of flow must now pass through a smaller area, fluid velocity head or kinetic energy must increase. After exiting the throat, the fluid enters the outlet cone, where the area returns to its original dimensions. As a result, the fluid decelerates to its original velocity. The energy required to create the increase in fluid velocity is provided by the fluid pressure head. So as fluid passes through the restriction, energy from pressure head is converted to velocity head. The result is that pressure falls. As fluid passes out of the restriction and decelerates, energy from fluid velocity is converted back to pressure head. Now, of course, there are no ideal restrictions. Even with a Herschel Venturi, which is nearly ideal, there is some loss of pressure head. This decrease in head is a result of energy being converted to fluid heat by internal friction. Let's look at a concentric orifice, which provides a close approximation of what actually happens in a valve. As the fluid passes through an orifice, it creates its own entrance and exit channels that are similar to those in a Venturi. The stream contracts to a minimum area just beyond the orifice. This is called the VENA contracta. Flow through a valve creates a similar pattern. We're interested in the vena contracta because its area is one of the values that affects the rate of fluid flow. The area of the vena contracta cannot be directly measured. As a result, flow calculations must rely on experimentally determined factors. For our purposes, these factors are all combined into one, called the valve flow coefficient, C sub V. You'll recall that flow rate through a valve is proportional to its experimentally determined flow coefficient. With a value for C sub V, the flow rate Q can be calculated using this formula, where G is the specific gravity of the fluid. Because the value of C sub V is determined by testing, it's only valid as long as actual flow conditions match those in the laboratory. Test conditions specify that lengths of straight pipe the same size as the valve are to be used as the valve inlet and outlet. The test also requires completely turbulent flow. Any change in this, or any change in fluid velocity or fluid viscosity, will have an effect on C sub V. Obviously, there aren't too many processes that match the laboratory test conditions. So a correction factor, the piping geometry factor F sub P, is used to account for any changes. For a real piping system, this is the formula used to calculate liquid flow through a valve. Later in this program, we'll be using this formula, but before we do, we need to discuss cavitation and flashing. That's because these can also affect flow through a valve. To understand how, let's examine each of these phenomena. We'll start with cavitation. As you may know, cavitation is a two-stage process: the formation of vapor bubbles and their subsequent collapse. Now, with that in mind, let's look at fluid pressure across this valve installation. These two lines illustrate the measured differential pressure across the valve. However, inside the valve, pressure can be considerably lower than the measured valve outlet pressure. The lowest pressure in the stream occurs at the vena contracta, just beyond the valve port. Now consider the instance where the vapor pressure of the process liquid corresponds to this line. Process liquid below this pressure is below its boiling point. With the proper conditions, vapor bubbles will form in this region. Then, after passing through the vena contracta, pressure recovery in the valve will cause the vapor bubbles to condense and collapse. As you may be aware, the implosion of these vapor bubbles results in noise and can cause extreme damage to the valve. Also, cavitation can reduce the capacity of the valve. Since the liquid passing through the valve port now contains vapor bubbles, the fluid density is reduced. Without a corresponding increase in fluid velocity, mass flow rate decreases. Effectively, the value C sub V is reduced. Fluid velocity can be increased by increasing the differential pressure across the valve. However, if the increased differential is obtained by reducing valve outlet pressure, the severity of cavitation will increase, and the effective value of C sub V will drop even farther. With a sufficient decrease in valve outlet pressure, flow will become choked. When flow is choked, a reduction in valve outlet pressure does not result in any increase in flow rate, only in additional cavitation. A continued reduction of valve outlet pressure will lead to flashing. Flashing occurs when valve outlet pressure is low enough that the vapor bubbles no longer collapse. The two-phase flow that results can directly cause physical damage and can lead to slug flow. Your text includes additional material on flashing and cavitation, as well as basic flow through valves. Stop the tape now. With an understanding of fluid flow fundamentals and of how the various types of control valves and actuators work, you have the basic knowledge necessary to properly make a control valve selection. The first step toward actually making a control valve selection is to understand the control objectives and determine how these objectives will be best obtained. If possible, meet with process personnel so that you can analyze the system together. Ask questions about the controlled variables, what their